对不起，我听不清楚。你说
您是叶老师吗？叶教授吗？
是，我是叶老师，好久不见了。
对，谢谢。
没有，感谢你过来帮忙。那等你准备好之后，我们就可以开始，因为已经9:10了，好不好？
好，谢谢，不好意思，我现在 I'm ready 了。
OK， 慢慢来，不急。
好，可以开始了。所以用英文嘛，哈。
就看黄老师自己就看方便吧，哈。有时候用英文，有时候用中文都可以的。
有没有外籍生在呢？
有。
Okay, now I'm gonna use that English, all right?
So you're going to stop now, right?
Okay.
Okay, go ahead. Thank you.
Okay. Good morning, my students. How's everybody today? So you can see the first page. My name is Ruichu Huang. I'm a faculty of Electrical Engineering Department of East Seoul University. Can I ask you a questions? Are you graduate students or undergraduate students? Anyone can answer me? Hello? Hello?
I think they are all graduate students.
Oh, they are graduate students. Okay. Yeah. Okay. Have you learned the fuzzy theory or neural network before? Because today the topic I'm going to talk about is a fuzzy neural network and its applications. So suppose you have the background of the fuzzy theory and neural network, then I think these materials probably will be a little simple to all of you. But if you don't have the background of the fuzzy theory and the neural network, then I'm not sure the content of this speech is okay to you or not. But anyway, we can see what's going on. Hello. So have you all the students, have you taken a fuzzy theory and the neural network before? Hello.
We are now.
Can you hear me?
Yes. This course is fuzzy theory, so we all know about the basic knowledge of fuzzy theory.
How about neural network? Hello. How about neural network?
I think some students will have background about the neural network, and some don't have.
Okay. Let's start my talk. Okay. Just like what I say, the title of my talk is fuzzy neural network and its applications. Okay. The first one I'm going to talk about is the fuzzy theory and neural network. We all know fuzzy theory and neural network have been applied in various fields successfully, especially in the control area. Why? Because both of them are treated as the parts of artificial intelligence. We say AI technology. Both have the ability to increase the intelligence of the system. And both of them just try to model the relationship between the input and the output system. So about this page, do you have any problem? If you don't have any problem, I'm going to continue the next page. So in general, I like to say both neural network and fuzzy system, we say have the ability to estimate, or we say model, an unknown system, especially unknown system. What do you mean unknown system? Unknown system means without knowing. the information or mathematical model of the system. Both can use the numerical methods to solve the problems. This allows us to use the mathematical tools to deal with, and it is easy to compete with the algorithms. Okay, let's take a review of neural network. So we say, what is neural network? Neural network, in Chinese we call 神经网络. It's a tech that can model the capability of the human's brain. Why? Because we all know human's brain is a highly complex, nonlinear, and parallel computer. It can execute the very complex work, such as the computation, pattern recognition, or we say computer vision, or decision making, or logic organization, and a lot. But however, the machine computer is just a machine with very high speed computation capability. It has no ability like pattern recognition, or do decision making, or do the logic organization. So that's why we say the aim of the neural network is to make the computer which has the capabilities of human's brain. And of course, we all know now neural network, we say it is a part of AI technology. So we may conclude that a neural network is a massively parallel distributed processor made up of simple processing units. The processing units usually we call neuron. In Chinese, we say 神经元, which has a natural propensity for storing experimental knowledge and make the neural network available for use. So it resembles the brain into two respects. The first one is, we say the knowledge is acquired by the network from its environment through a learning process. And then interneural connection strengths, sometimes we say known as the synaptic weights, or we just simply say weights, are used to store the knowledge we obtain. So at here, is there any questions? Okay. So next page, you can see, I just show you a very simple basic structure of neural model. So usually, this is a 3-layer neural network. In general, the neural network has two necessary layers. One is called input layer. The input layer, we just input the data. The data we're gonna train. And then the output layer is just send the output, the desired output, or the output information about the data. And next one we call the hidden layer. We call it 隐藏层. But usually, how many layers of hidden layers is depend on the user design. You can use 2 hidden layers, or 3 hidden layers, or 1 hidden layers. So how many hidden layers is probably, it depends on the data is big, or it's complex, and also it's a nonlinear or nonlinear. So we said benefits of neural network. So how many benefits about neural network? Here we conclude name as the first one is non-linearity. We say an artificial neuron can be linear or nonlinear. So the neural network can perform a nonlinear signal processing. And the second, the neural model can do the input and output mapping. Mapping, that means find a relationship between the input and output pairs of the data. So we say the neural network can automatically develop relationships between input and output pairs. And the third one is adaptively. That means the neural network has a built-in capability to adapt its weights to fit the change of the surrounding environment. The next one is called fault tolerance. The neural model, say, if it is implemented in the hard forms, we say it has the potential to be inherently fault tolerant in its performance, because like we just mentioned, because knowledge is distributed equally in the weights. Therefore, the neural model still can perform well, even some damages happen in the neuron or its connection. So that's why we say the neural model has a higher fault tolerance. The next one is we say the VLSI implementations, because the neural model it has a massive parallel nature. So such a nature can make the neural model potentially faster for the computation of certain tasks. So these some features makes a neural model ideally suited for implementation using we say the very large scale integrated technology. Here we say VLSI technology. That means actually in the future a neural model is very suitable for VLSI hardware implementations. So above these benefits the neural model has. So next one, I'm going to talk about neural network learning. You know, actually, learning is a process by which the three parameters, or we call weights, of a neural model are adapted through a process of simulations by the environment in which the network is embedded. So this means neural model just like the human's brain. We just take the learning from the environment we are surrounded. And the type of learning is determined by the manner in which the parameter change. So here you can see we say the learning types. Usually there are two learning types of the neural model. One is supervised learning. What means supervised learning? That means 指导式学习. That means learning with a teacher. It also means there is a teacher will teach the neural model and teach him how to feed the data and obtain useful information from the data. So from these block diagrams, you can see we say the training data or we say historical data will be sent to the neural model. Of course, in the training data, we all have a desired output information. So the neural model takes the learning. It will usually get output. Then we compare the desired output and the actual output. We can get an error. So this error will be sent into the neural model to take the weight adjustment. So that means learning. This is the learning process of the supervised learning. The next one is we call unsupervised learning. Unsupervised learning, that means the learning without a teacher. So usually the supervised learning, we call it as self-organized learning. That means, okay, you can see here, we say learning without a teacher. So we just send the training data or historical data to the neural model and then get the output. So usually, what's the output information? We don't know. Certainly, we don't know. Maybe just take a feature extraction, or just can classify the training data into different categories, something like that. Okay, because just like at the beginning, I asked you, do you have the background of the neural models? So because here I'm gonna give you a summary of error-backed propagation learning algorithm. Actually, usually we say this is a BP learning algorithm. This is a very popular learning algorithm used in the neural network. So in general, we initialize, if we want to take a error-backed propagation learning algorithm, we have the following steps. The steps one is initialize a weights, omega, to small random values. Usually the values is between minus 0.5 to 0.5. But however, this is just a kind of suggestion. You also can use or other values or other random values, or you just set the initial weights of the neural model are all 0. That's fine. The step 2 is now we present the first input and output data into the neural model. So here you can see we present an input and specify the desired output. Then we calculate the actual output using the present value of weights. So we can get the output. And then because we get the output and we also have the information of desired output, that means we can compare these two outputs and get an error. So the step 4 is find out error terms. We call delta. Okay, the delta J is for all nodes because for each node we all have error terms. And here we say if DJ is called desired output of the J's output nodes, and OJ is the computed value of the J's output nodes, and XJ is the computed value for the J's hidden nodes. Then for an output nodes, this is the error term for the output nodes. It's equal to DJ minus OJ multiply OJ and multiply 1 minus OJ. So here you can see DJ minus OJ is the actual error from the output nodes, and then OJ multiply E minus OJ. Actually, this part is from the we said from the derivations, not derivation, actually from the algorithm of the sigmoid function. We just take the steep descent algorithm, and for this part, it's just different differentiation parts from the sigmoid function. Okay. Then for hidden layer nodes, because now delta J is XJ multiply 1 XJ, so you can see just similar OJ multiply 1 minus OJ. So this is for the XJ and multiply 1 XJ. This is the output of the hidden nodes, and then the summation delta K omega K, this is the error terms sent back from the layer above the hidden layer. So for example, like the output layer. So because in this part we use the summation, that means probably in the output layer we have multiple output. We have the, for example, we have the three output in the output layer. That means we can get 3 error terms. But suppose we just use 1 output node in the output layer, then the symbol summation will be disappear. Then we just get the omega multiply omega weights. So here you can see the we say the K is over or nose in the layer above node J. And then we take the adjustment of the neural weights by using this formula. So we say the omega ij of n plus 1 is, that means the next weights, is present weights omega ij of n, and then plus alpha delta j yj, and then plus eta omega ij of n minus omega ij minus 1. Here we can say n plus 1, n, and n minus 1. Index next, present, and the previous, excuse me, respectively. And next step 6 is present another input, and then go back to the step 2. That means we just send the data in the trained data set one by one. Suppose now, for example, suppose we have 10 pairs of input and output data in the data set. So from the first one, input output data to the 10th input output data, when we finish this 10 data, that means we take one times learning, or usually we say one epoch. Okay, so but usually, so how many epochs we have to take for the neural model? So it depends on how complex or how nonlinear of the trained data. So above is contents is about the neural network. Is it okay to all of you? Yeah, do you understand?
Yeah, okay.
Okay, so now let's take a review of fuzzy system. Right? So what's the fuzzy system? We know the fuzzy theory is initiated by Lotte in year 1965. So what's mean a fuzzy? Fuzzy actually it's defined as a broad, imprecisely defined, or we say confused, or we say weak. All this means it's not clear, or it's not uncertain. So it is fuzzy. And then why we want to use the fuzzy system? Because we all know in the real world there are too many things are complicated. So that's why we say the real world is too complicated for precise descriptions to be obtained. Therefore, we need an approximation, or we say fuzziness must be introduced in order to obtain a reasonable or traceable model. So when we are moving into the information era, human knowledge becomes increasingly important. Therefore, we say we need a theory to formulate human knowledge in a systematic manner and put it into engineering system together with other information like mathematical models and sensory measurements. So if you have the experience like working in a factory, I do believe you all heard about expert experience. So sometimes you ask someone who is a senior engineer, so why did you want to do this? He will tell you, oh, you just follow my way or something like that. He cannot explain its way very clearly or use a mathematical model to tell you why. So that means such kind of knowledge is based on the experience. So this is the actually, this is the concept of the fuzzy system we're going to use. So we say usually fuzzy systems are knowledge-based or rule-based system. We call fuzzy if-then rules. So what's mean by if-then rules? That means if A is what, then B is what, something like that. So we say fuzzy if-then rules is an if-then statement in which some words are characterized by continuous membership function. So the starting point of constructing a fuzzy system we say is to obtain a correction of fuzzy if-then rules from humans experts or based on the domain knowledge. So the collection of fuzzy if-then rules, then usually we create the rule base. Then we combine these rules into a single system. It's called a rule-based system. Different fuzzy systems use different principles for these combinations. And from the fuzzy history, we say usually there are 3 types of fuzzy system. The first one is the most simple one. It's we call the pure fuzzy system. And second is the Takaji's Juno Ken. We say TSK fuzzy system. Third one is fuzzy system with the fuzzifier and the defuzzifier. Actually, now this fuzzy system with fuzzifier and defuzzifier is the most popular fuzzy system in the world. It's popular used in industrial application, or we say in control engineering. So here I just show you a fuzzy system with fuzzifier and the defuzzifier. You can see the fuzzifier. The fuzzifier means we just transform the real variable into the fuzzy state. So this is the input. And what's mean the defuzzifier? Defuzzifier means we transform the fuzzy state, because in here the fuzzy mechanism include 2 parts. One is fuzzy rule base, the other one is fuzzy inference engine. Actually, these 2 parts are used to compute fuzzy calculations. And then we get the fuzzy output. This fuzzy output will be sent into the defuzzifier. Defuzzifier just transform the fuzzy set into a real variable to the output. So we get a real variable at the output. For example, suppose you want a controller, you want to design a fuzzy controller, and probably the output of the controller is the electric voltage or electric current. It must be a real value. Okay, the next one, let me show you why we say we want to combine the fuzzy and the neural model. So for this part, just let me show you an examples of a fuzzy controller design. So this in this example, you can see, suppose now we have 2 systems. However, here, because these are just a study, so we say we consider a nonlinear system given by the following equation here. This is for equations, because this equation are used to do the simulation. But in the real world, we can assume, or we can suppose, this system is an unknown system. We only know send the input to this system and then get the output. Yeah, okay, and then the second example is consider an unstable nonlinear system. described by the following equations. So here you can see we have two state equations and then one output equations. Now we want to design a controller. So the U of k is a control input. So we use the control input to control these two systems to get the output, the desired output we want. Okay, this is a fuzzy rule base with a linguistic variable. So that means you can see we create a fuzzy rule base. That's we use the arrow k and the arrow change to be the two parameters. Here we said NB and SZ PS PB. That means arrow. If arrow is negative big, negative small, 0, positive small, positive big, and the arrow change is negative big, negative small, 0, or positive small, positive big. Then depends on the different condition. In this table, you can see there are 25 rules in the table. So for example, suppose we say if arrow is negative big and the arrow change is arrow negative big, then the false is negative big. Okay. For example, if arrow is 0 and the arrow change is negative small, then the false we use is negative small false. Okay. Actually, this rule base is created by the usually we say by the experts. However, in the control area, this rule table is very standard. It's almost I mean, it's most popular used by the control researchers. So here you can see now we just set the membership function. For example, suppose at the beginning we don't know what kind of membership function is the best for the controller. So we just use a very simple and triangular membership function for the arrow and arrow change. So that means for these examples, we use the same membership function for the arrow 10 and arrow change 10. And the value is from the -1 to 1. And for the U of k, the defuzzifier, here we use the singleton membership function. So no matter it's UK or delta UK, we use here you can see negative big and negative small, 0 or positive small, positive big. So, but however, here we use P1, P2, P3, P4, P5 to standard these 5 conditions, and the value is -10 to 10. So, okay, the minus that means negative false. The plus 10 is positive. The positive values means use the positive false. Okay, and also in this fuzzy mechanism, we say the fuzzy control mechanism developed is basically composed of by the following parts. The fuzzifier, we use the triangular membership function, and the inference engine, we use the product inference engine, and the defuzzifier, we use the center average computations. So for this example, we said 2 controllers will be developed and simulated. One is the output of fuzzy controller is the force U of k directly. The next one is the output of the fuzzy controller is the increment of delta U of k And then the false is U of k equal to U of k minus 1 plus delta UK. So from here, these two parts, you can see one controller just send the control false directly. The other one controller is will send the false increment, and then the real false is the increment, the false increment plus the previous false to be the exact, or we say the actual false. See the yellow part, the yellow membership function is the membership function we use at the beginning. So for the first one problem, you can see the control performance is this red line. So this red line, you can see the rise time is 8, and the overshoot is 1.0743, and the steady state error is 0.0743. Of course, at here we just want to do the position control, and we just want to control the output to reach the 0.1. So from these parts, you can see this is the control false. Is U of k. So just like what I say, this is very standard and very simple of the membership function set by the controller designer. But however, what kind of membership is the best for the controller? We don't know. So sometimes before we just use the manual operation way to adjust the membership function. So you can see if we adjust the member function, for example, right here, for the error 10, the member function is just as this one, and the delta error terms, the membership function of the delta error terms is adjusted as this one. Then we get the output of the equation or output of the system we want to control. It's just like this blue line. From this blue line, we can say its performance is much better than the red lines. However, you can see here, we still have the steady state error is 0.0137. But I would say from this part, from the membership function to become the membership function we showed here, probably we will take a lot of time to try it. Okay, and next one, you can see if we design a controller, the control force is increment of U of k. So the red line is the performance of the based on the simple membership function at the beginning, and the red line is the performance once we use the manual operation to change the membership function from red part to the blue parts. You can see both of them can perform and make the steady state error of the system is 0. But however, for the first one, you can see we have a very large overshoot. The overshoot is about 1.6, and the settling time is 29. Okay, and for here, you can see for such a controller, looks like a blue line. We use this kind of membership function, we can get a very not bad, very good controller to control the system. Of course, the problem one is a very simple system. And then, so here we say the above example just show that appropriate Lua base and the appropriate membership functions are the key factors that determine the quality of the controller effect. However, basically, just like what I say, the manual adjustment based on the experience will take a lot of time. Too many try and error steps will be taken. So we say, suppose if the fuzzy mechanism have a self-tuning ability, or that means if we make the fuzzy mechanism have the AI technology, it can tune take the self adjustment about the membership functions. Then we say this controller, we don't need to spend a lot of time to tune the parameters of a fuzzy mechanism. Just let it to tune to take the self tuning, and then will make the controller performance will be excellent, something like that. So that's why we say how to make the fuzzy mechanism have the self-adjusting capability. Like a neural model is the main purpose of the development of fuzzy neural network. This is also the title of this speech. We say fuzzy neural network. Okay, so let's see. Before we talk about the combination of these two technologies, we say what kind of similarities between neural network and the fuzzy system. We say both neural network and the fuzzy system have the ability to successfully estimate a system without knowing the mathematical model of the system. This means without knowing the information of the system. The neural network can only come into play if the performance is expressed by a sufficient amount of observed examples. So these observations are used to train the black box, we say the unknown system. On the one hand, no prior knowledge about the problem needs to be given. That means we don't need to any knowledge about the problem we're going to solve. On the other hand, however, it's not straightforward to extract comprehensive and clear rules from the neural network structure. Of course, on the contrary, a fuzzy system demands there are linguistic rules instead of learning example as prior knowledges. And the input and output variables have to be described by linguistically. So let's mean you can see the fuzzy rule base just like the neural weights. Okay. So how to make the rule base can be adjusted by a learning process and make a fuzzy system like the neural network is the purpose of the fuzzy neural network technology. So, and then we say, next one, we say if the knowledge is incomplete, then the fuzzy system must be tuned due to the wrong, or we say contradictory result, since there's no any formal approach for it. The tuning is performed in heuristic ways. This is usually very time-consuming and error-prone. So for this part, like just what I say, if you want to change the Lua base, because usually Lua base is described by the heuristic ways. if you want to change the lower base, then I would say you got to have lots of experience to do the control design, and usually such kind of tuning will takes a lot of time, and you have to take a try and the error and the try. So we say lots of try and error will be taken. So from here, you can see how we say both neural model and the file system have something in common. So both of them can be used for solving a problem. If the given problem, or we say the given problem is unknown system, has no any information or for any mathematical model. Therefore, how to use both concepts, taking their advantages and then eliminating their disadvantage is the main purpose of the development of fuzzy neural network. So here, let's see, just give you a simple one. We say in the neural model, the learning process is to find the proper weights to make the neural fit the environment of surrounding, or we say to fit the model of the trained data. So you can see usually the learning is in the learning process, or we just take a lot of weights of adjustment, like I show you in the error back propagation learning algorithm. So we say the increment of weights, delta omega, ij of n. But however, you can see for these parts, because in the neural model, we just we use the back propagation learning algorithm. We just send the error 10 layer by layer to adjust the weights. Here we just use error 10. So now we suppose if we can create a fuzzy mechanism, we use the error 10 and the error change to make a fuzzy system to be like a weight tuning mechanism. So that means this part, this increment of weights is generated by the fuzzy mechanism. So that also means we can use the fuzzy mechanism to do the weights of the weights adjustment of the neural model. So you can see the new weights can be the current weights plus the increment of the weights generated by the fuzzy mechanism. So this is just, we can combine these two advantages of these two models. So for this one, we use the fuzzy mechanism to do the weight adjustment. So what's the next one? Next one is in previous example, I just show you. We say the membership function, or we say lower base, are both adjusted by using the error back propagation learning algorithm. So let's you can see in the previous example, we say how to make the membership function from this one to become a better one, or become a best one. So actually here we can use the error back propagation algorithm to adjust either the membership function, or the other one is either can change the lower base. So now I'm going to talk about is we call a fuzzy neural network. So here we say the hybrid neural fuzzy system, or we say fuzzy neural network, is homogeneous and usually resemble neural network. Here, the fuzzy system interpreted as a special kind of fuzzy neural network. The rule-based fuzzy system is interpreted as a neural network, and the fuzzy set can be regarded as weights, whereas the input and output variables and the rules are modeled as neurons. Neurons can be included or deleted in the learning steps. Finally, the neural network represents the fuzzy knowledge base. You can see here, we say, here, let me just show you, or we just explain you a very famous fuzzy neural models we call ANFIS. What's mean ANFIS? It's an adaptive network-based fuzzy inference system. So we say the architecture and the learning procedure underlying the ANFIS, the fuzzy neural model, is a fuzzy inference system implemented in the framework of adaptive networks. We use, we say, by using a hybrid learning procedure, the ANFIS can construct an input-output mapping based on human knowledge. That means in the form of fuzzy if-then loops and stipulated input-output data pairs. Okay. Here is a figure of the ANFIS model. In this model, let me ask you, you can see it here, actually, this figure just shows a complete fuzzy computation process of the fuzzy system. So you can see when I input for example, here is the membership function for the arrow. Here is the membership function of arrow change. Then we take the product inference engine. So we use pi. Then we just use the node pi as the neuron. So this here, you can see we take the pi calculations. Okay. Then this is for the process of inference. The layer 3 actually is normalization. It's a part of the center average, the defuzzifier process. So we this one we take the normalization process for the output of the output for the pi products. And the last one is just use you can see just the center average when we get the probably weights for each loose file. So here, then we just take, at last we take the summation of the loose fired based on different weights. Then we get an output. So suppose, I mean, if you know the fuzzy system and you know how to operate like a fuzzy controller design or fuzzy system design, suppose you know such kind of operation procedure very clear, you can see actually this neural model. Usually we say it's a neural model. However, it's just draw the whole process of the fuzzy computation to be a neural model style. Okay. So here you can see we can change these two weights. Once we get the arrow, we can send the arrow back to change these two weights. Okay, since these two weights, that also means you change the rule base. because F1, F2, just like the variable P1, P2 are used. Okay, so when you change this part, that means you change P1, P2, or that means also you change the lower base. And then if you change this part, that means you change, if you change the weights at here, that means you change the membership function shape. Okay, like the example from the standard, a very simple membership function change to into the an appropriate, or we say a good membership function shape. Okay. So let me here. Let me show you two examples of fuzzy an application. Okay, the first one, application one, I just say it is a modified self-tuning fuzzy neural controller for the nonlinear model reference control system. Okay, for this application, we say because simplicity of and the sobriety in the real control applications, fuzzy controller has been widely employed into many linear and nonlinear control systems, especially for the system whose information is uncertain or unknown. The fuzzy controller could incorporate the use of human knowledge in the fuzzy mechanism, and basically fuzzy control can be classified into the non-adaptive, or we call a conventional, traditional fuzzy control, and the other one is adaptive fuzzy control. In non-adaptive fuzzy controls, the relevant parameters of fuzzy controller are fixed during its real-time operation, like the shape of main function is fixed, the lower base is fixed, no matter the control performance is good or not. So we say all the parameters of the fuzzy mechanism are fixed during its real-time operation. This one we call a non-adaptive fuzzy control. Therefore, we say a good and effective fuzzy controller is very difficult to be designed for a complicated system if the highly accurate performance is desired. So usually try and error is the method we are known for the parameter adjustment, just like the example I show you. And then we say the main advantage of adaptive fuzzy control is the better performance can be achieved due to the control's parameters could be adjusted to fit the environment changes. Since the stronger incapability and adaptability, neural network technique has been applied in the area of adaptive fuzzy control. So this one is a very simple structure to describe the fuzzy neural control system. You can see here is a fuzzy neural controller. We control the system, or we say the plan we will want to control. From the output of the plan, we get an error tone. Then we send the error tone by using the adaptation loads, or we say adaptation weights, to adjust the parameters of the fuzzy neural controller. So in this example, you can see I say in order to speed the reaction power of fuzzy neural controller. In this application I show you, we only use line rules. So only line rules are taken to construct the Lua table. And then the membership function of fuzzifier for error tone and error change tone. And the defuzzifier for the false increment are shown in the following table and the figures. So that means you can see unlike a traditional fuzzy controller, usually they use 25 rules in the rule base table. And here you can see I just use for the error turn, we have the negative, 0, and the positive. Error change also use negative, 0, and the positive. So the false we use also have only 9 rule base. Here you can see suppose error is negative, delta error is negative, then the false we use is negative false. The error is positive and the error change is 0. That means the false we're gonna use is positive false. So this one, you can see this is the memberships function we designed for the error k and the delta error k. And the false, we use negative false. For example, compare with the previous the example here, like we use -10, 0, and u of k, u of L plus 1 is +10. So negative false, 0, and positive false. We just simply, at the beginning, we just simply use such kind of very standard membership function, and for falsifier and for the singleton membership function for the defalsifier. So here we say for making the controller have the adaptability, the strength of firing rules. That means the rule base. The rules are in the rule base. So the rules firing, the strength of rules firing, and the singleton values of the defalsifier are designed to be adjustable. So both of these two can be adjusted based on the controller performance, the control error. So the whole fuzzy computational process is organized to be a neural model. Okay, the next figure will show you such kind of model. And the steep descent gradient method is used to derive the tuning algorithm. So that means the error back propagation algorithm will be taken to adjust the fuzzy parameters. Okay, so this is the control figure I show you. Actually, this is very similar, only which is exactly like the fuzzy ANFIS model structure I just show you. So here we say this is a falsifier, and at the beginning it will send to the falsifier. That means membership function. We send these two terms in the membership function, and then we take the inference in the product inference engine to product the membership values get from the membership function, and then we take the normalization and then multiply the rules. The rules are on the rule table. That means the rules are fired on the rules table, and then we get the summations. Actually, this center average defalsifier average algorithm to get the output. The output is the output false is the increment of false, and then based on the error 10, we just tune in these two parts, these weights. These weights, so we say delta 1 to delta 9. That means just change the value of the rule base, and also at this part we change the change the weights omega. So here this means we change the membership function of the falsifier. So here let me show you some example. The example one is this one is two-order unstable linear system given by the following equations. And all initial values of the variable are set to be 0. That means all initial conditions are 0. And this is the unknown system, or we say unknown plane. we're going to control. And we say the system is requested to follow a model given by this model. Actually, this reference model. And here, you say the list reference model here, the reference input of k. Of k is expressed by this equation. Of k is equal to 0.5 sine of 0.007k plus 2 cosine 0.059k. Okay. We actually, in this example, we want to control the output. Control the output of this system to follow the output of this reference model. So this is actually here is not we just not a fixed point control. It's become a reference model control. So you can see, okay, this is first the controller performance. You can see from this figure. In this figure, we just plot the superposition diagram of the control result on the first simulation. Here, the dashed line is the output of reference model, and the solid line is actual system output. Well, you can see it's hard to distinguish of these two lines. That means at the beginning, only at the beginning, when fuzzy controller is adjusting, is to be adjusted, then you see, you can see a little you can see the blue line and red line. However, after probably after several times tuning, then the controller can control the plan to follow the reference output very well. Example 2, it is two-order learning system. Okay, here is a two-order control system. So we want to control this system to follow the model given by this equation. This ym model is here, and here uc of k is a function. Also, it's a function. So f uc of k is 0.6 sine pi uc of k plus 0.3 sine 3 pi uc of k, and then plus 0.1 sine 5 pi uc of k. uc of k is sine 2 pi k over 250. So here, this is the reference, the description of the reference model. Then the fuzzy controller, fuzzy neural controller, we want to control such kind of unknown system to follow the output of this reference model. Let's see. So send us a previous example. Actually, at the beginning of you can see here also the output of reference model is dashed line. The solid line is actual system. So at the beginning, probably you can see these two lines difference. But about probably 40 steps or 30 steps, then the controller can control the output to follow the reference model. Very well again. And then the example 3 is a high order learning system given by this equation. Again, we want to control this equation to follow the reference system given by this equation ym. Here, r of k is for the different steps, different times. R of k have the different values. Again, next one is the superposition diagram of the control result on third simulation. So again, dashed line is actual the output of reference model, and the solid line is the actual system output. So you can see the fuzzy controller also can control the system to follow the reference output Very well. Again. So in the first application, I just show you the fuzzy neural controller to control the nonlinear system to follow the reference model. Okay. Now let me show you the application 2. Actually, application 2 here, the title I just call it Adaptive Fuzzy Controller Design on Simulated Moving Bed. What mean simulated moving bed? Simulated moving bed in Chinese, we called 模拟移动床. Okay, what's the function? What's the purpose of the simulated moving bed? 所以模拟移动床的目的是在哪里? Okay, let me see. Let's see. With chromatography, it's a method which is used to separate the constituents of a mixture based on the individual components' character. Actually, SMB has been widely applied into chemical and biomedical industries, especially for the biomedical area. Okay, here I might explain this part in Chinese to all of you. Chromatography 就是我们叫做晨曦分离。晨曦分离事实上就是用来分离化合物或者是混合物的一个工具。它可以把两种混合物分离起来，然后呢把它分离出来。这个我们叫做晨曦分离。它事实上在actually before we want to do the process of chromatography, sometimes we just use a pipe. 在以前我们可能只是用一个试管在做，那试管在做不但速度慢，而且效果不好。如何把一个试管呢变成一个连续的试管，就是变成说you can see 我们叫做 moving bed. It's called a moving bed. So simulated moving bed, it is an advanced technique, or we say become an advanced technique in the chromatographic separation process due to its continuous operation abilities. B will become a continuous operation process. So that also means SMB will become a continuous process that can provide significant quantities of the purified or enriched material at a low cost. So that means 如果我们用这个连续性的 moving bed， 就是模拟移动床，因为它已经变成一种连续操作的一个晨曦分离的方法，所以它可以产生大量的，也就是在晨曦分离的量上面可以增加，而且呢，它因为用的水跟这个吸附剂比较少，所以它可以在一个比较低成本的方式之下操作。So here you can see, just show you for example. So here, for example, this is actually we have 8 columns. So columns, 一个 column 就是一个试管 for example. So this is the picture for the 8 columns SMB system. So when the columns, for example, at this part we feed a mixture with 2 material A and B, fit here, and then we have refinate B plus D, and over here we can extract A plus D, and then we just control make this 8 column to move like a circle. to make it just make it to move like this way, and make it become a continuous process. So actually, this research aims to develop an intelligent control mechanism for simulated moving operations. And we say a smart control mechanism based on fuzzy theory for SMB system is studied. Actually, here we say SMB dynamic mathematical model is deduced from the true moving bed. The mathematical model of SMB can be described at least two partial differential equations. Actually, I want to tell all of you, because these two partial differential equations is nonlinear, and it's very hard, and all we say probably it is impossible to solve these equations. So that means the clear or the model of the SMB system is impossible to be obtained. So we cannot use such kind of, use the traditional controller to control the SMB model, because the real model of SMB cannot be derived or to be obtained. Okay, this page is just show you some definition of these symbols, the index, okay, for these two equations. I think I don't need to explain to all of you for each variables. For example, I is components of mixing, J is the J's segment, and X is the moving direction and distance, something like that. I don't need to explain it to you one by one. You can just read it by yourself. Okay, so just like what I just said, we say, in fact, due to the complex and the nonlinear characteristics of the simulated moving bed, the closed form of SMB system cannot be obtained. Therefore, an adaptive and a precise control mechanism for SMB is still hard to be developed so far. So how did you design a controller to control the SMB system well? Is the aim of this research. So in this research, we say at the beginning, we just take an approximate and the digital SMB system is developed first. Such a digital, we use numerical ways to derive the approximate model of SMB or SMB system. We say such a digitalized simulation SMB system can approximate the real system. Therefore, this approximate model then can be used to design the control mechanism for SMB system. So in this study, an adaptive fuzzy neural controller for SMB system is designed. And this controller is used to control the relevant parameters of SMB for improving the efficiency of the SMB separation operations. So in this figure, you can see same as the ANFIS I show you, and also very similar. Very similar. Actually, the figure is also same as the figure I show in the fuzzy controller in the previous example. But however, in this part, you can see the membership function for arrow and the arrow change and the pi operator. And actually, this part is not correct. It's incorrect. Okay. Actually, this part is not pi. Pi operator is here, so this part is normal. It's n nodes. That means we take a normalization of the weights and then multiply the Lewis file and then get the control force. So actually, like what I said, we should correct this expression, these nodes by n nodes. Okay, then we say in this study, the SME structure used in this study was 2, 2, 2, 2. That means we have 8 columns. In 4 section and 8 columns. In each section, we have 2 columns. So the extract outlet was said to be the purity of material B, and the refinate outlet was the purity of the material A. So that means we have to separate a mixture with 2 materials A and B. So we say then the following figures. The following figures show the purity changes of the 2 substances controlled by the adaptive fuzzy neural controller. The first one, okay, the first one in the first control result, we can see, for example, here. Suppose we design the desired purity of material A is 0.9. Then the fuzzy controller can control the SMB to get the purity of material A is about, okay, it's about, let's make it bigger so you can see it's about 0.8966. It's almost 0.9. And then if we say the desired purity for material B is 0.9, also we can see the fuzzy neural control can control the SME to get the purity of B is 0.998. So it's very, very close to the 0.9. The next one, also the next one is suppose we for this SMB system, suppose we set the desired purity for material as 0.92. Then the control output we get from material A, the purity is 0.9186. And then if we set a desired purity of the 0.96, then we get the output of the material B. The purity of material B is 0.9559. So you can see these two these two values, these two outputs are also very close to these two desired purities. Okay, and then next one is again, suppose we set desired purity is 0.94. Is for the materials A, and for the materials B is 0.95. Then we get the actual purity of the SMB system. For material A is 0.9411, and for material B is 0.954. Okay, at last, for the material, if the desired purity is 0.94, we get the actual the purity of material is 0.9413. For the materials B, if the desired purity is 0.96, then we get the actual purity of material is 0.9538. So here we conclude that we say this research present the smart control mechanism based on fuzzy neural controller for the linear system. And from the simulation results, we can say results show that the complex learning system indeed can be actually controlled by the adaptive fuzzy neural controller. It means the fuzzy neural controller has a great ability in dealing with the nonlinear control applications. Actually, the fuzzy neural controller indeed has a great potential in the real industry applications. Okay, so my talk is finished here. So students, do you have any questions about my talk? Hello.
老师，我
Hello，
用中文问可以吗？
可以啊，可以，没问题。
就是那个，所以我们这个 fuzzy 的部分是用在决定 neural network 的权重是吗？
不是，你现在讲的是第一部分还是第二部分？
第一部分。
第一部分这个部分你可以去做，但是我会不建议你用 fuzzy 去做全值的调整。您懂我意思吗？为什么我不建议呢？你可以去研究，可以去做研究，但是你知道神经网络在做全值调整的时候，我们都希望我们的 AI 系统，它的除了要准之外，另外一个应用大家都知道，你要快，你懂我意思吧？要快。那你全值调整，你看我们在 BP，我们 BP 的方式，好，我秀给你看，在前面，我们传统的 BP 在调整的时候。我很快的秀给你看一下，我们传统的 BP 在调整的时候，当我们数学式子，就是说我们根据那个所谓的steep descent，我们叫做老师中文突然忘记，我们就是用这种斜坡陡坡下降法。当我们把全值的调整公式调整完之后，我们得到误差，我们马上就用这个公式去修正了，对不对？对不对？这是我们神经网络一般修正的方式。
对对。
但是我刚才讲了，你可以用fuzzy 来调这个神经网络的全值，但是我说我不推荐。为什么我不推荐？因为你要知道，我们你看我们一般在做这个模糊系统的运算的时候，我们先要把误差送到membership function 归属函数里面去找出对应值来，对不对？然后我们要回头去看我们启动了哪几个规则，对吧？然后我们再经过正规化，再经过解模糊化，我们才会得到我们的全值的修正量。我的意思也就是说，在这个部分，今天我用的是三角形的归属函数。三角形归属函数事实上来讲，每次你大概只会启动10条规则库，但是很多人他用的是高斯函数连数型的归属函数，那意思就是表示你每一次25条规则库你都要启动，所以你的计算的时间会花的比较多。那你计算时间花的比较多，你再去调整每一次全值做神经网络全值的调整的话，就回到这里，你会让神经网络全值的调整会变得比较慢。但是当然我讲了，就是说你如果是做研究，去试看看，可以。那一页，不好意思，我看看哈，这两个，在这个部分，如果你用模糊系统来做全值的调整的话，你看看会不会比传统 BP 方式的，因为传统 BP 方式只用误差量而已，我们这里不但用误差量，还用了误差的变化量，所以误差量是代表实际的 output 跟我期望的 output 之间的一个距离，那误差的变化量就代表速度，也就是表示说它不但考量了误差的距离，也考量了误差变化的速度。所以当你用这个东西，也许你用 BP 要调整，我举例子来讲，你单一用误差的变化来调整，也许你需要调整500次或1000次，当然这跟你的学习速率的设定也有关系。那你如果同时考虑误差跟误差变化量，看会不会能够说学的次数比较少，因为这里就不会用到 learning rate， 这里可能就不会用到你的一个，当然你要加一个 learning rate 也可以那你这里可能就不会有所谓的学习速率的设定那我讲过，你要加一个学习速率设定量也可以。那我是说，你做研究上面你可以那来做做看也许试试看这两种方式的不同，但是真正在应用的时候，其实我不建议，它会比较慢。我这样回答可以吗？
了解。所以老师，你前半部的那个都是在讲就是研究上的，
你说这里吗？
对对对。 就是你实际应用不会这样。
我这么讲好了，实际在用的 fuzzy neural 来讲，是把 neural 的概念用到模糊系统里面去，你懂我意思吧？这个就是我们的 fuzzy neural。是的，那并不是讲说把 fuzzy 用到 neural 里面去。这一部分来说，就是像这样子，我们知道一定是可以，你懂我意思吧？我们知道可以，但是我们要考量，就是说它在运算会不会花比较多的时间？当然花比较多时间，我就讲了，就不一定需要用。那我刚才说了，你看我们刚才讲都是把 neural 的概念、neural 调试的概念用到 fuzzy。那 fuzzy 在运算的过程，你刚才说了也会经过就是我们叫做规则化就是 membership 归属值的运算，然后呢要经过 rule base， 然后再经过简模化这样的运算过程。我们现在只是把这个整个模糊计算，本来我模糊计算的过程里面，我们把它画成一个好像神经网络的结构。这边是归属函数的对应，我们算归属值，然后呢，我们用乘积式的推论引擎 reference engine， 然后呢，我们再取 normalize 再取正规化，然后乘上所激发的这些规则库，然后经过简模化去summation 出来得到所输出。其实你可以看到，这每一步事实上就是在你做一个模糊系统的时候，它所用的步骤，只是我们把这些步骤用这种方式把它画出来。所以你可以看到，像在最后一个图形，我这边都是给它画圈啊，圈，这边也是画圈，这边就让大家看起来好像每一个圈就是代表一个神经元。事实上，它就是整个一个就是我们在做模糊系统设计的时候的一个过程而已。那这时候我们可以用 BP 的方式去调整这些圈值，调整这个圈值就是代表你调整规则库，规则库里面的这些启动的规则的大小，然后呢调整这个圈值呢就是在调整这个圈值就代表因为你归属值出来，当你去调整归属值就代表你的归属函数，你所对应的归属函数被调整了，也就代表你的归属函数的图形事实上是改变了。你懂我这意思吗？
我懂，所以不是把 fuzzy 用在 neural network， 是取 neural network 的概念。
对，取 neural network 概念，然后去做这里的调整，这里调整，就变成说我让这个 fuzzy system 它有自己调整的功能了，像 neural network 一样，而不要用手动的去调。手动去调你要试，你可能要试千百次，对不对？才会找出最好的。那这个东西呢，就让它自己去调整出最好的出来。这样了解吗？
好，了解，谢谢。
OK，any more questions？ 还有没有问题？那假设没有问题，我今天的 talk 就到这里结束了，好不好？
同学们还有没有其他问题呢？同学们还有没有其他问题呢？没有的话，我们就谢谢黄老师。
叶老师，谢谢你哦。
好，谢谢你，下次再约你吧。好
，OK，拜。
好，同学们，那我们今天的课就到此为止。有问题可以 email 给我或助教。那我们就下课。
好，谢谢老师。
好，谢谢
老师。
谢谢老师。拜拜。
OK，拜拜。